Hello guys, this is Dimedin and today we're doing Edexcel IAL Chemistry Unit 1, October 2021. So let's get right to it. So question number 1. The maximum permitted concentration of sulfur in diesel fuel is 10 milligrams sulfur in 1 kg of diesel fuel. What is this concentration of sulfur in ppm? So to calculate ppm, we have to do the mass of the solute, which is the mass of sulfur, mass of solute, divided by mass of solution, which is the 1 kg of diesel fuel, and then we times that by a million. 6 zeros. Okay, so mass of the solute, so that's 10 milligrams, so that's going to be in grams, 10 times 10 to the power of minus 3 grams, all over mass of solution, which is kilograms, so that's 1 times 10 to the power of 3, and then we times that by a million. So 6 zeros. Alright, so when you do 10 times 10 to the power minus 3 over 1 times 10 to the power 3 times a million, we will get 10. So our final answer, the concentration in ppm, is C10. Alright, then the next question says 3.2 kg of this diesel fuel is burnt in air. What is the maximum volume of sulfur dioxide which can be produced, measured at room temperature, and the total mole volume at 24 dm cubed? Okay, so we know that 1 kilogram contained 10 milligrams of sulfur, right? So using that logic, we can say that 3.2 kilograms of fuel will contain 3.2 times 10, which is 32 milligrams of sulfur. So all we have to do is now work out the moles for this. So moles, we know the N of sulfur, the moles for this will be, so mass of sulfur, which is 32 times 10 to the power minus 3 grams, because of milligrams, all over, so the relative atomic mass of sulfur is 32, and then what do we get? We get the moles is 0.001, or 1 times 10 to the power minus 3 is the same. And now since we know the moles, what we can do is work out the volume. Now the volume we know is going to be, so volume is going to be 24 dm cubed for a mole, so times that by 0.001 moles, that'll give us 0.024 dm cubed. Alright, so the final answer is A. Okay, let's move on to the next question. Question number 2. Which equation represents the second ionization energy of chlorine? Now, we know that the first ionization of something, right? So in this case, Cl will be no charge, right, of gas, goes to Cl plus gas plus E minus. That is the first ionization energy. The second ionization energy would be Cl, right? Cl plus, like, so we take this, and this goes, and this becomes our next ionization energy. So this becomes Cl plus, so gas, goes to Cl2 plus gas plus E minus. So this right here is the second ionization energy. So now we need to look for something that's similar to what we have here. Okay, so we have Cl plus gas goes Cl2 plus E minus. So it's not A, right? It's not B, not C. Cl plus gas, Cl2 plus gas plus E minus. So this is it. So not A, not B, not C. It's D. So our final answer is D. Alright, now question number 3. The diagram shows a mass spectrometer. So this is the mass spectrometer here. Which process occurs in region R? So now region R, okay, so let's look at what the options are. The sample is vaporized using a heater. Now that's false because the sample is already vaporized. So that's already false. So already vaporized before it even enters the mass spectrometer. So what we can do is we can cut this option. So this is not what we're going to do. The electrons are removed from the molecule or atoms and positive ions are formed. Now this looks plausible because you can see there's a plus sign here. That means that the electrons are attracted to this side of this side, and then they follow through. So let's see what C says. So electrons are added to the molecules and negative ions are formed. Now this is just false because negative ions are not formed, and D ions are accelerated by an electric field. Now that is region S, not region R. Region S. So our final answer will be B. So that's our final answer. Alright, which statement is correct for region T? Region T, okay, that's region T. Ions with a greater mass have a smaller deflection. Ions with a greater mass have a greater deflection. Ions with a greater charge have a smaller deflection. Ions are speeded up by a magnetic field. Now we know that lighter ions are deflected more than heavier ones, right? More than heavier ones. What else do we know? We also know that if we have a larger charge or a greater charge, that can also lead to greater deflection. So if you have greater charge, that will lead to more deflection. So having said that, let's look at the options again to see which ones we can use. So let's look at the answers again. So ions with a greater mass have a smaller deflection. Now is this true? We know that lighter ions are deflected more than heavier ones. So heavier ones are now deflected less. So we know this is correct. Let's look at this. So ions with greater mass have a greater deflection. That's false because we just said it's a smaller deflection. Ions with a greater charge have a smaller deflection. That's false because you can see over here, greater charge, more deflection. So that's false. Ions are speeded up by a magnetic field. That is region S, not region T. So our final answer is A. So let's move on to question number 4. So a mass of 0.23 grams of sodium was added to 350 centimeter cubed water to form hydrogen and a solution of sodium hydroxide. So Na solid, H2O liquid, NaOH plus half. What is the concentration mole per dm cubed of sodium hydroxide in the solution form? So let's look at the molar ratio here. So you can see over here that this is a 1, so 1, this is 1, and that corresponds to 0.5. Okay, so now that we can see it's a 1-to-1 ratio. So first we have to find out the concentration of this. We need to first find out the moles of sodium that's being used. So let's do that. So the moles of Na will be what? So mass over molar mass. So mass is 0.23 grams over molar mass is 23. So this gives us 0.01 moles of sodium. So we can write over here, so 0.01 moles. So we should get 0.01 moles of sodium hydroxide, right? So now N equals CV. Now we want concentration, so C equals N over V. So we know that the moles are 0.01. What about the volume? We know the volume is 350 centimeter cubed over here, but we are looking at dm cubed, so this will be, in dm cubed will be, so 350 centimeter cubed into dm cubed will be dividing by 1000, so 350 divided by 1000, so that would be 0.35. So that will be 0.35. So this gives us 0.02857, and if you were to round it, we will get 0.029. So let's look at our answers. You can see over here that is B. Okay, so let's move on to part B. Part B says, what is the maximum volume in centimeter cubed of hydrogen which could be formed. Okay, so let's look at that. So we know that let's look at the molar ratio again. So you can see that if we have 0.01 moles of sodium, so that will be 0.01 moles of hydrogen. This will give us 0.005, so divided by 2. So let's look at that. So that's pretty easy. So we know volume is usually what? Moles. So they're asking in centimeter cubed. So this would be 24,000 centimeter cubed because we times by 1,000. So times by 24 cm cubed. So the moles we know is what? 0.05. So that's pretty straightforward. 0.005 times 24,000 cm cubed. So once you put this in the calculator, so 0.005 times 24,000, this gives us 120 centimeter cubed of hydrogen which could be formed. So our final answer will be A, 120. Alright, so let's move on to part C. Part C says sodium hydroxide solution was neutralized with sulfuric acid. Which is the ionic equation for this reaction? And this is actually a trick question. If you remember, acid plus base, right, equals salt plus water. And we know that the ionic equation for these reactions are always H plus OH minus gives us H2O. So all of these are irrelevant. And the only one we care about is A. It's a trick question. It'll save time if you know the trick. So for all neutralization reactions, this is the ionic equation. Alright, so let's move on to part D. Part D says sodium hydroxide was added, solution was added to magnesium sulfate solution. The equation is shown below, so you can see over here. What is the atom economy by mass for the production of magnesium hydroxide? So how do we work out atom economy? So atom economy, that's usually what? So it's obviously a percentage. So what's percentage of what? It's usually, so the MR of the desired product, right? So I'm just going to desired over MR of total products. Okay, so times by 100. Times by 100. So let's look at that. So what is the desired? So we want magnesium hydroxide, right? So that's going to be Mg. So that will be 24.3 plus. So it's two of them. So hydroxide. So O plus H. So 16 plus 1. So that is our desired. That is our MgOH2. Okay, the total would be, so it'll be the same thing again. So it'll be this. Okay, so it'll be this plus we have Na2SO4. So Na, so we have two of them, so 2 times Na, which is 23, plus SO4, so what's S? S is 32.1, plus 4 oxygen atoms, so 4 times 16, so that's that. Okay, so the top part is 24.3 plus 2 times 16 plus 1, that gives us 58.3. And if you do the bottom, you'll get, so that will be the first, so Na2SO4 will be 142.1 plus 58.3 from above, and we times by 100. So this should give us the atom economy. The atom economy is 29.09%. And you can see over here, all of these are rounded to one decimal place. So if we round it, we will get 29.1%. So you can see over here 29.1%, and you can see A is also 29.1%. Alright, so that is the answer. Let's move on to question number 5. You can see over here, it says, in which series are ions in order of decreasing ionic radius? decreasing. Okay, so they're saying, so this column is the smallest. This should be the smallest. That's what they're saying. So let's see if that's true. You can see right off the bat that AL3 plus is smaller than Mg2 plus and Na plus. So A is off. What about B? Li plus is also the smallest here. So that's also wrong. What about C? N3 minus, O2 minus, and F minus. And F minus is indeed the smallest. So this over here is the smallest. So let's look at the last one. O2 minus, S2 minus, Se2 minus. So this is going down group 6, and that is going down, so it's going to increase. So D is also out. So our final answer is C. Okay, so now it says a stable ion M3 plus contains 18 electrons. So M contains what? Say, so it's 3 plus, that means we took away 3 electrons, so it should contain 21 electrons, right? Okay, so then it says, in which block of the periodic table is element M found? So what we can do is we can go straight away and just write down the electron configuration. So let's do, so 1s2, that's 2, 2s2, that's 4, 2p6, that's 10, and then 3s2, that's 12, 3p6, that's 18, 4s2, that's 20, and then 3d1, so that's 21. So all of them added will give us 21 electrons. You can see over here that it ends in the D, so it's going to be in which block? It's going to be in the D block. So that our answer is C. Alright, let's move on to question number 7. Ammonium iron 2 sulfate, NH4 2FeSO4 and 6H2O is a double salt that is used as a source of iron 2 ions. What is the relative formula mass of the double salt? Okay, so that's pretty straightforward. All we have to do is add everything up. So you can see there are 2 molecules of NH4, so 2 times, so N is 14 plus 4 hydrogens, so that's just 4 times 1, which is 4, plus Fe, which is 55.8, plus, so 2 SO4 molecules, so 2 SO4 is 32.1, plus so we have 4 oxygen atoms, so that's 4 times 16, plus what? We also have the 6 water molecules, so 6 times H2O, so that's 2 plus 16. Alright, so let's simplify. So this will be 2 times 18 plus 55.8 plus 2 times 96.1 plus 6 times 18, and that will give us a 36 plus 55.8 plus, so that is 192.2, so 6 times 18, which is 108. This gives us, so we add them, 36 plus 55.8 plus 192.2 plus 108, but in the calculator you will get 392.0. So that's our final answer. Let's see if it's in here. That is C. So our final answer is C. Then it says ammonium sulfate is used in preparation of double salt. What types of bonds are present in ammonium sulfate? Ammonium sulfate. Now let's look at it. Let's draw what ammonium sulfate would look like. So ammonium sulfate would actually look like this. If we draw what it looks like, then it might make sense. So we have plus hydrogen, hydrogen, hydrogen. Then we have another, we have 2 of these molecules. And inside we actually have, so S double bond O here, S double bond O, O, O. And this is -2. So this is actually, you can see over here that this is ionic bonding here present. And then you can see over here that there is also there's a dative bond. The dative bond present, and you can see here between the N and the H, that's also a normal covalent bond. So what's present? Ionic, dative, and covalent. So it's always easier to draw it out to see which ones are present. So that is D. Let's look at part C. Part C says, what is the total number of ions present in 0.1 mole of the double salt? Now let's look at the double salt. What are they? So we have two molecules of NH4. So we have 2 times NH4, right? What else do we have? We have Fe, right? We have Fe, and we have 2 molecules of SO4. Let's look at that. So we're talking about the ions here, right? So 1 times Fe, and we have 2 times the SO4, 2 minus ion. All right, so that's that. Let's now look at the ions present. To define the ions, we have what? 0.1 moles, right? Times by 6.02 times 10 to the power of 23 to get the number of molecules present, right? In the double salt. And then you times by 5 because you have 2 plus 1 plus 2 to get the 5 ions, right? So this will give us 3.01 times 10 to the power of 23. So our final answer will be 3.1, so that's C. Alright, so that's part C done. Let's move on to question number 8. In which series are the elements in order of increasing melting temperatures? So increasing melting temperatures. Okay, so let's go. A, iodine is a solid, and F2 is a gas, so that's not increasing temperature, that's decreasing. What about Li? So we have Li, Be, boron, and the carbon. Carbon is fairly hard to melt compared to lithium. It's a very soft metal, so this is probably right. Let's move on to the next. C. Let's look at C. So Li, Na, rubidium. So this is going down group 1, and Li has the greatest increasing. So this has the lowest. This is lowest melting point in the series. What about D? So Si, Ps, and then chlorine. Chlorine is again a gas, so that's not increasing melting temperature. So the final answer will be B. So that's that. Let's move on to question number 9. So which row gives the polarities of the S to F, so it's sulfur to fluorine bond, and the SF6 molecule? Now it's always easier to draw the molecule. So we have S, right? Then we have 2F, we have an F here, and then we have something like this, F, and something like this, F. Then we have the other ones, which is F. So this is a 3D molecule, SF6. Now the molecule itself is nonpolar, right? The molecule itself, so the molecule itself is nonpolar, but the bonds, so the SF bond is still polar. So we need to find polar. So polar, polar in the SF bond, and the polarity needs to be nonpolar. So nonpolar, nonpolar. So you can see we have double ticks in B, so our final answer is B. Over here. Alright, so now let's move on to question number 10. Methane reacts with excess chlorine in UV light. Which process occurs in the initiation step? So if you remember, in the initiation step, we have usually it's Cl to Cl, and I usually have the half arrows like this. That's how I usually look at it. So let's see. So part A, there's double arrows. There's only one of them. So no. Option B. So we have Cl, Cl. You can see that there is 2 half arrows. This is probably the right answer. C has a double arrow, so no. D, the arrows are coming inward, so no. So the answer is B. That is our answer. Then it says in the next question, part B, which of these molecules could not be formed in a termination step. So C2H6 can be formed, CH3Cl can be formed, CH2Cl2 can be formed. DHCl can be formed? No, because this is in the propagation step. This is used up in the propagation step. So we can say DHCl is our answer. Let's move on to question number 11. Geometric isomerism is shown by 2-chlorobut-2-ene. What is the skeletal formula of E2-chlorobut-2-ene? Now, an easy way to remember this is, I always remember this as that we have E isomers and Z. And Z I usually name it as same or same. So how I remember it is that we have the molecule and this goes down. This is our Z, right? It's the same group. And if you have E, that's going to be, so that's our Z. So our E should look like, this should be Cl up top. Should be like this. So this is what 2-chlorobut-2-ene should look like. Let's see what's the similar one. So is it D? It's not D. Is it C? No, C is Z2-chlorobut-2-ene. So no, B is not there. So it must be A. So our final answer is A because it's the same as what we have drawn here. Okay, now it says, what is the total number of sigma bonds? What is the total number of sigma bonds in Z2-chlorobut-2-ene? So now it's talking about Z, right? Now it's talking about Z. So what you can do is you can actually draw it out. So I'll actually draw it out for you, so it's easier to see. So we usually have, so we're going with this. We are going to draw this, and this is Cl. So let's actually draw this. This will be our C double bond C. There'll be C, H, and H. And then C is bond to Cl, and then we have another C, H, and H. Alright, so what you need to remember is that the C double bond C is not actually one sigma bond, it's actually a sigma bond plus a pi bond. And then we need to remember that as carbon to a carbon bond is only a sigma bond. And then you need to remember that the carbon to a hydrogen is also a sigma bond. Well, but what you're probably not familiar with is a C to Cl bond is actually not one sigma bond, it's actually worth two sigma bonds. So having said that, now what we can do is we can just highlight what we want to know. So this is a CH bond. CH, that's 1, 2, 3. This is another bond. So we're just highlighting what we want to do here, right? So what are the bonds? And then we can go ahead and you can just name them. So CH we have said is sigma. So sigma bond here, sigma bond here. Carbon to carbon is also sigma. Carbon to double bond to another carbon is sigma plus pi. Carbon to Cl is 2 sigma. Carbon to carbon sigma. Carbon to hydrogen sigma. Carbon to hydrogen sigma. Carbon to hydrogen sigma. So all we have to do now is add them up. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 sigma plus pi. So how many sigma bonds are in total? 11. So our final answer is 11. Let's move on to question number 12. So they're telling us that this question is about chlorides of beryllium and calcium. Complete the electronic configuration of the atoms of beryllium and calcium using the SPD notation. So beryllium has how many electrons? It has 4 electrons. So that will be 1s2, so that's just 2s2. Page forward. Calcium, on the other hand, calcium has how many electrons? It has 20 electrons. 20 electrons because it has 20 protons. So that 1s2, that's 2s2, so that's 4. 2p6, so that's 10. 3s2, so that's how much? So 2, 4, that's 12. And then we have 3p6, that's 18. And 4s2, now that's 20. Now we can just confirm. So 2 plus 2 plus 6 plus 2 plus 6 plus 2. That's 4, 6, 10. 10 plus 2, 12. 12 plus 6, 18 plus 2. This is 20. So that is correct. So this is our final answer, 2s2. And 2s2, 2p6, 3s2, 3p6, 4s2. Then they ask us in the gaseous state, beryllium chloride is molecular. Draw a dot and cross diagram to show the bonding in a molecule of beryllium chloride. That's pretty straightforward. All we do is just draw a circle. That is for beryllium, and then we draw another circle over here. Copy, you can just paste it. Alright, so now we can just say, so this is beryllium, this is chlorine, this is chlorine, and so let's use crosses and dots. Alright, so that's the 4 electrons of beryllium, and then the dots are used for the chlorine, so we have 7 of them. So we have this, and then we have 7 on this side as well. So that's how we get the 2 marks, to get 4 in the beryllium and 7 for our chlorine in total. Alright, let's now move on to part C. In the solid state, beryllium chloride formed the polymeric structure. The diagram shows a part of the structure you can see over here. The diagram uses lines and arrows to represent the 2 different types of covalent bonds. So arrows our dative bond, and our BeCl, this line, is our normal covalent bond. Describe how each type of bond is formed. Okay, this is pretty straightforward. All we have to tell us is that the arrow, so arrow is a what? Arrow is a what? It's a coordinate bond or a dative bond. So coordinate bond or dative, whichever you prefer. And then we have to describe what it is, right? So coordinate bond, so this is which is what? Which is when we have a lone pair, right? Lone pair of electrons. In this case, the lone pair of electrons are donated from chlorine to what? Which atom? From chlorine atom to which atom? To the beryllium atom. So chlorine to beryllium atom. So that's our arrow. Now we have to talk about the line. So the line is a what? Is a covalent bond. Covalent bond. Now what do we talk about? Covalent bond. How would we describe a covalent bond? This is which is when what? Electrons come from both chlorine and beryllium. They're essentially sharing electrons, aren't they? That is what the covalent bond is. Beryllium atom. So what are the 2 marks? So the 1 mark is stating that air is a coordinate bond and then explaining what it is. Second mark is saying that line is a covalent bond and then explaining what a covalent bond is. Those are 2 marks. Let's move on to part D. The Cl-BCl bond angle is different in the 2 forms of beryllium chloride. Okay. Predict the 2 bond angles, justifying your answers by referring to electron pair repulsion theory. So as a gas, right? As a gas, this side is molecular. So as a gas, BeCl2, right, will probably look something like this. So if we draw our BeCl2 molecules, right, we will actually get 180 degrees here. We'll get 180 degrees. Because why? Because this is BeCl2, there are no lone pairs, so we have to talk about, so this is a gas, so BeCl2 what? Contains what? Contains 2 bonding pairs, right? 2 bonding pairs. And How many lone pairs? You can see there are no lone pairs, so no lone pairs. So what type of shape would you call this? This is a linear shape. So no lone pairs. So this is a linear shape. All right. So the bond angle we've already said it's 180. So we can just say it's the bond angle. The bond angle, just to emphasize, would be 180 degrees. And then what? We have to say because, right? Because why? Because now we state our electron pair repulsion theory, because the bonding pairs, right, repel each other. This is the electron pair repulsion theory. Repel each other to minimize or maximum. So you either write minimize repulsion, or you write to maximize separation. So either would do. Alright, so now if we take BeCl, so if you look over here, now we're taking, let's say we take one of these chains, one of the part of the chains. So that'll be BeCl, right? So Be, then we have Cl, and then we have Cl here, Cl, and Cl here. You can see here that in this molecule, how many bonding pairs are there? 4 bonding pairs and 0 lone pairs, right? So what we can say, so now we can say the other part. So we can say, if we take, so this was a gas, so now we're talking about the solid structure, right? The solid state. Solid beryllium chloride. What about that? So contains what? Contains, as we said, 4 bonding pairs, and then what? And 0 or no lone pairs. So the shape would probably be tetrahedral, right? But because it's a polymeric chain, all we need to know is the angle, right? And the angle for a tetrahedral shape is usually 109.5. So all you have to tell them is that the angle would be, and the bond angle would be 109.5. So that's the end of that question. So what you will get 1 mark for stating the 2 bonding pairs, no lone pairs, and then stating that it would be 180 degrees. And the next part would be to talk about the electron pair repulsion theory, which we did over here. Third part would be to either the bonding pairs, and then giving the angle will be the 4th mark part of it. Alright, so that's part D. Let's look at part E. So it says, anhydrous calcium chloride is a crystalline ionic solid which melts at 772 degrees Celsius. Draw a dot and cross diagram for calcium chloride. Show the outer electrons only. That's pretty straightforward. So we draw calcium atom here, and then we draw our chlorine molecules here. This will be, so we have a Cl, and then we have 1 cross, let's say for calcium, and then we have 7 dots, so this is a minus, then another over here, so this is also a minus, so C is obviously a 2 plus, so this is our 2 marks. So 1 mark for Ca2 plus and 1 mark for getting both Cl, right? Alright, so that's that. Let's move on to question part F. Explain why gaseous beryllium chloride and solid calcium chloride have different types of bonding. Okay, so what can we talk about here? So what can we say? What do we know? What are the differences that we know about beryllium and calcium? We know that calcium is further down the group, so it has what? More shells, right? What else do we know? What else do we know? That because it has more shells, it has what? It has a less polarizing power. Less polarizing power. What else do we know? What else do we know about the differences in two in relation to bonding? Bonding, how can we get covalent character? What is covalent character dependent on? Character dependent on, is it dependent on what? Electronegativity. So which one of these two are more electronegative? Is the one that's more further up the group, right? Which is beryllium. So we can say this is less electronegative. So less electronegative. So these are three reasons. Let's now put them into words. So we can start off by saying, so calcium has what? More shells, right, than beryllium. So what? Because it has more shells, the outer electron is easily removed. Then beryllium, so its outer electrons are more easily removed than what? Than beryllium. Okay, why is that? Because now we talk about our polarizing power. Because calcium C2 plus ion is less polarizing than what? Than the beryllium 2 plus ion. Okay, so now we know that electronegativity determines whether a compound shows covalent character or not. Then we can say beryllium chloride shows more covalent character. And why is that? Because we said more covalent character, which is the same thing saying covalent bonding in this case, right? Covalent bonding, more covalent character than calcium chloride, obviously, which we are always comparing, which is, ionic bonding in this case. And then we explain why. That's because what? Because, right, this the key thing here, because what? Calcium is less electronegative, right? These were the reasons we first talked about. So the reasons were more shells, right? So outer electrons are more easily removed. Why? Because Ca2 plus is less polarizing than B2 plus ion. The last part is that shows more covalent character because calcium is less electronegative. So those are our 3 marks to explain why beryllium chloride and solid calcium chloride have different types of bonding. Then move on to question number 13. So this says, this question about silicon and carbon. Silicon is a semiconductor. Data obtained using mass spectrum of silicon are shown. We have the isotope number 28, 29, 30, and then its respective relative abundances. Calculate the relative atomic mass to 2 decimal places. This is pretty straightforward. All we have to do is do 28 times 92.17% plus 29 times 4.71% plus 30 times 3.12%. Pretty straightforward. All we have to do now is 28 times 92.17 over 100 plus 29 times 4.71 over 100 plus 30 times 3.12 over 100. So let's put this in a calculator. So we will get 28 times 92.17% plus 29 times 4.71% plus 30 times 3.12% will give us, so this gives us 28.11 because it says 2 decimal places, so 2 dp. That's our final answer over here. So one more for the working out, one more for the answer. So now it says, suggest a reason why there's a small peak in the mass spectrum of silicon at MZ14. Now 14, right? Now relative is usually 28, right? So there must be a correlation between 14 and 28. The only thing I can think of is that the atoms which were atoms of mass 28 maybe had a charge of 2 plus. Had a charge of 2 plus, right? So because it had a charge of 2 plus, it would have deflected to give us a value of mz, to give a value mz of 14, because 28 divided by 2 is 14, m divided by z, right? So that's one suggestion. If you have any other suggestions, I think they'll be equally as sufficient, but I think this is the best suggestion you can talk about so far. Let's move on to part III, which I've already done here. You can see that isotope Si, so 28 Si has how many protons? It has 14 protons. 29 has 14. The protons don't change, but the neutrons do. So 14 plus 14 is 28. 14 plus 15 is 29. 14 plus 16 is 30. So that's our answer for this table. So next we have silicon dioxide, the main constituent of sand, and has a giant lattice structure similar to that of diamond. Crystalline silicon dioxide is used as a surface for semiconductor devices to provide a heat-resistant electrically insulating layer. Explain how the structure and bonding of silicon dioxide makes it useful for this application. Now, if you remember diamond, right? What do you know about diamond? It's similar to diamond. So diamond, well, the qualities of diamond is it's what? It has a very high melting point. That's a key of diamond, and also it's also a bad conductor of electricity, right? So you can say it's insulator, so electrical insulator. Okay, so why is that? It's a similar shape, isn't it? Why is that? Well, we can say, right, first of all, when we talk about the structure. Now, what is the structure? It is so SiO2 is a what? Is a giant covalent structure. So first we talked about the covalent structure, right? This is the structure in the first part of the question. Now what do we talk about? So giant covalent structure, we talked about that. What else do we know? It's held together by covalent bonds, right? And these bonds are very hard to break, right? Why? Because of this high melting point, right? It's very hard to break. So this is a very high melting point. So what we can say is, so these covalent bonds are what? These are very hard to break. Are very hard to break. So as a result, what happens? As a result, requires a lot of energy, right? Requires a lot of energy to do what? To break them. Making it what? Very heat resistant. Making it very heat resistant. So get rid of this. Very heat resistant. Okay. So we talked about the heat resistant bits. We have talked about heat resistant. We talked about the bonding. And now we have to talk about what? We're left with electrical insulation. Now, how do we talk about the electrical insulating bit? You can see here there is no delocalized electron to carry the charge. Delocalized electrons. So that's all we have to talk about. We can say that there are also no delocalized electrons to carry charge. To carry charge. Carry charge where? Carry charge across SiO2, right? Like the molecule carry charge. So this makes it, makes SiO2 an electrical insulator. So those are the points. So we talk about it's a giant covalent structure. Then we talk about that it requires a lot of energy to break the bonds. Then we talk about there are no delocalized electrons to carry charge, and that's why it's a good electrical insulator. So that's how the thing works. Let's move on to part C. All right, they tell you that calcium silicate is formed in the removal of silicon dioxide impurities, and then a sample of calcium silicate is composed of calcium, silicon, oxygen, and they have given us 12 grams of calcium, 8.43 grams of silicon, 14.47 grams of oxygen. Determine the empirical formula of calcium silicate. So what I always do is we put calcium here, silicon here, and then oxygen. First I'll look at the grams we have available. So what's available? So we know the mass, so I put mass. Mass is what? We have 12 grams versus silicon is 8.43 versus 14.47. And what about its molar mass? Because we want the moles, so this is now molar mass. So what's the molar mass of calcium, which is 12 over 40.1. Silicon is what? That is what? It's over 28.1. And then oxygen is what? Oxygen is 16. Okay, so 12 over 40, so now we need to find the moles. So the moles are 12, 40.1 is 0.299, which is we can round to 0.3. 8.43 over 20.1 is 0.3. 14.47 over 16 is 0.9. So now we divide all of these by 0.3. So when we divide them, we will get what? 1 to 3. So our empirical formula will be calcium 1, silicon 1, and then O3. So that's our calcium silicate, SiO3. Empirical formula. Pretty straightforward. Let's move on to part D. So we have carbon dioxide is a gas at room temperature. Phase of drink is counted 5 degrees Celsius and pressure 1.3 times 10 to the power 5 and contains 3 grams of carbon dioxide. Calculate the volume in centimeter cubed occupied by 3 grams at 5 degrees at this pressure. They want volume, so now they've given us the equation. So let's now rearrange. So V equals N times R times T all over P. Okay, so we don't know N right now, right? But we can find everything else. So what do you know about R? R is 8.31, so we know this. What T? T is in kelvins. So you can see over here, so that would be 5 plus 273 to give us 278 kelvins. What about our P? Our P is, they've given us 1.3 times 10 to the power 5 PA. Okay, now let's work out the moles of carbon dioxide. So we know we have 3 grams of this, the mass. What about the molar mass? So that's carbon is 12 plus 2 times the oxygen molecule, which is oxygen atom, which is 2 times 16. That's 3 over 44. That gives us 0.06818, and this is just recurring. So you just leave it at 6.06818. Now let's plug in everything in. So V will be 0.06818 times 8.31 times temperature, which is 278 Kelvin, all over pressure, which is 1.3 times 10 to the power of 5. So when you put this in the calculator, we'll get 1.2116 times 10 to the power of minus 3. What, centimeter cubed? Nope, it's in meter cubed. But we want the answer in what? We want it in centimeter cubed. So how do we change that? So we know that from going from meters to centimeters, we times by 1,000. So going from meter cubed to centimeter cubed, we have to times by 100 cubed. So volume will be 1.2116 times 10 to the power of minus 3 times 100 cubed. So once we do that, we will get 1211.6 centimeter cubed. So we can just round it. V equals 1212. Just round it to a whole figure, centimeter cubed. The accuracy doesn't matter as long as it's not one significant figure. I always recommend just do 3 or more, just to be precise. That is our answer for question number 13. Go on to question number 14. Aluminium is an abundant metal with many uses. The first 4 ionization energies of aluminium are shown. So we have ion 1, 2, 3, 4. So you can see it jumps from 578 to 1820, and then similar jump to 2750, and then it jumps straight to 11,600. So we can say over here that, right, what can we talk about? So we have this first jump, the second jump, and then the third jump, right, between the levels. So first, second, and then third. You can see there's a greater increase in the third and fourth ionization energies, right? So we can say, right, there is a greater increase between what? Between the third and fourth ionization number. So this indicates what? Which means that there are 3 electrons in the outer shell. There are 3 electrons in the outer shell. So that's all. So we have to talk about the difference. There's a great increase, and that there are 3 electrons in the outer shell. That's our 2 marks. Let's go to part B. So we have the graph show the first ionization energies for the elements in period 3. So you can see over here. Okay. Explain the general increase in the first ionization energy from sodium to argon. So this increase, so we can just say, what can we talk about here? We know that what's increasing, right? What's increasing as we go along here? The proton number is increasing, right? Proton number. Is there anything else that's increasing? No, there isn't. So all we can say that number of protons increases, right? What else? If the number of protons are increasing, we still have the same level of shielding. So that's something else you have to add to get the second mark. And there is same shielding. That's all I need to say. So we'll get proton increases and same shielding. Okay. Next we have explain why the first ionization energy of aluminium is less than the first ionization of magnesium. We need to talk about what? Now we're talking about shells, aren't we? So sodium starts with what? Sodium starts with, so it starts with 3s1, right? I'm just going 3s1. Then we have 3s2. Then we have 3p1. We have 3p1. Then 3p2, 3p3, 3p4, 3p5, and 3p6. Okay, So the ones we're looking for are the 3s2 and the 3p1. Right, that's what we're looking at. So you can see over here that the 3p1 has a lower ionization energy. And why is that? Because the 3p1 electron, right, from aluminium, what about this, is shielded by the s electrons, so it's easier to remove, is shielded by the s electrons, the one earlier in the first Na and Mg, s electrons. So requires less energy to remove, requires less energy to remove. So that's one mark. And then what are we comparing this to? We're comparing it to, compared to the 3s2 electron from magnesium. That's it. Talked about the shielding and which shells we're talking about. So it's shielded, so it requires less energy, right? We shield it all the way here, and we're comparing it to 3s2 electron. That's our 2 marks. Move on to part CI. So describe the bonding in aluminium metal. So what bonding are they talking about? This is a very simple question. If you think about it, this is just define metallic bonding. That's what they're all about. Define metallic bonding. Okay, so that's pretty straightforward. So what happens in metallic bonding? So this is when we have a sea of delocalized electrons are attracted to what? In this case, we have a aluminium cations are attracted to a lattice, right? The keyword lattice we have to use here. So lattice of aluminium. So an aluminium, because we're making specific cations. Cations are also the same thing as, if you remember, positive ions. 2 marks are sealed delocalized electrons surround the metal attracted to the lattice of aluminium cations. So give 2 possible reasons why aluminium is used for overhead power cable. Now this is just down to memory. It's very simple. Aluminium, there's lots of uses and qualities of aluminium. Aluminium is lightweight, right? That's one reason. Lightweight. It's also ductile. Like this is my 2 marks already, but I can go on. We can also say it's is a good conductor of electricity. So that electricity. All right. Now it says part DI, new uses for aluminium waste, aluminium cans are being investigated. One possible use is making nanoparticle alloys to produce hydrogen for fuel. Aluminum nanoparticles react with water to produce aluminum oxide and hydrogen. Complete the following equation. State symbols are not required. Okay, so we make AL, we make hydrogen. So first let's write hydrogen. We make hydrogen. And we make aluminium oxide. Now aluminium oxide is usually Al2O3. Okay, because we have Al2O3, we have 2 Als here. So that would be 2 Al over here. And what about the oxygen? We have 3 of them on Al2O3, so 3. So how many are we left with? We're left with 3 here as well. Okay, now it says part, so that's our answer. So now it says give 2 possible reasons for producing hydrogen from aluminium rather than from fossil fuels. It's pretty simple. For when we look at fossil fuels, all we have to talk about is say that fossil fuels are non-renewable. Like that's easily a 1 mark. Non-renewable, unlike water. That's 1 mark. And what about if we produce hydrogen? What does it do to the environment? We know that producing hydrogen instead of burning fossil fuels, so producing hydrogen this way reduces what? Reduces greenhouse gas emissions, right? Gas emissions. And how is this helpful? It's helpful because which helps reduce global warming. That's all I need to talk about. Reduce global warming. Okay, so the two marks are non-renewable, unlike water, and it reduces greenhouse gas emissions, which in turn helps reduce global warming. Pretty straightforward. 15A. Alkanes are obtained from crude oil. Describe how a sample of octadecane can be obtained from a mixture of alkanes. Now, whenever I think of crude oils, I always think of fractional distillation. In this case, they're asking for a sample, so with a mixture of alkanes, so we can just use fractional distillation, right? So you can say the mixture is fractionally distilled. Yes, fractionally distilled. So that's a 1 mark. What about next? And then we can collect different fractions, right? Different fractions at different temperatures. Right? Where do we collect them from? From the fractionating column. From the fractionating column. Alright, so the first mark is mixture is fractionally distilled, and then what happens? So we can collect it at different fractions, different temperatures from the fractionating column. Alright, now we're taking an octadecane can be cracked to produce butene and one other product. Complete the equation. State symbols are not required. So you can see here that we're taking away, so C18 goes to 2C4H8, so we're taking away 8 carbons and 16 hydrogens. So what are we left with? So C18 minus 8, that's going to be C10. How many hydrogens are we taking away? 16, 38 take away 16, that's going to be 22. So that's our answer. So let's move on to part II. One of the products is butadiene. Gives skilled formula for other 3 alkenes of C4H8. So first let's draw them, and then we can convert them into skeletal. So butadiene, so we have so butadiene, so this either goes up, so that's our Z, or it can go down. Sorry, that's our E, and goes down C. Or we have C, and then it's a double bond C. Okay, and then the rest are obviously hydrogens surrounding it. Same thing here. Yeah, there's one too many. Okay, so 4. And same thing here. These are all hydrogens. Okay, so now to convert them into skeletal, so that will be this, and then we have a small here, and then we have the double bond down here, and then we have double bond here. Okay, pretty straightforward. So those are our 2 marks. Let's move on to part III. So we have some products of butadiene are shown. So butadiene adding chlorine, butadiene adding steam, nickel and hydrogen, and KMNO4. Give the structural formulas of each products. And okay, so let's first realize what we're talking about here. So this is halogenation. Okay, so product 2, how do we get that? That's hydrogenation. What about KMNO4? That's oxidation. We're adding oxidation. This is oxidation reaction. What about product 4? We get that from hydration. Okay, now that we're familiar with the reactions, let's first draw it normally, and then we can draw it structurally if we're confused. So the CH3, when we add product 1 would look like, so we have C, and then we have C, and then we have another C here. So this would be Cl, this would be Cl, because the double bonds are now opened up, and the rest are hydrogens. So hydrogens, and hydrogens. So that's product 1. So name would be 1,2-dichlorobutane, right? So the name would be, so we can write 1,2-dichlorobutane. Now we want the structural formula, so that would be, so CH3 in the first, so that would be CH3. Then we have the CH2 as before. Then we have CH and then Cl, you can see over here. So we have CH and then Cl here, CH2 and then Cl here. So all we have to write down is, CH, Cl, and then CH2, Cl. Okay, that's fine. Let's look at product 2. That's hydrogenation. And now because we're adding hydrogens, right? So that's pretty simple. All we need to remember, this will give us an alkane. In this case, that will be butane. So this would be butane. Straightforward. So it'll be CH3, CH2, CH2, and then CH3 at the end. Okay, pretty straightforward. Look at product 3, that's oxidation. So we should get, so instead of the Cl's, right, we should get, so it'll be very similar to what we did over here. So this would look like, so we have C, but instead of the chlorines, we have OH, and then the same hydrogens. Hydrogens. And then how would we describe this? How would we name it? Same thing again. So that'll be, so instead of 1,2-dichloro, you'd say in when you talk about alcohols, that'll be butane, and then you're at 1, 2, and then you're at diol, because there are 2 of them. So how would we name them? Same thing. Structural formula would be same thing as 1, but instead of the Cl, now we add our OH. So CH3, CH2, CH, OH, and then CH2, OH. Okay, now let's look at product 4. Let's look at product 4. So now we're adding steam and we're adding H+. Now this actually will give us only one OH group. So this will be, so if we were to draw it as C, and C, we're left with our normal hydrogens, and then over here we have our OH, and then normal, and CH. So what is this? This is what butan 2-ol, right? You can see a second carbon. So butan 2-ol. So that would look like, so we said again, so it's the first, it's fine, CH2, and then the third one, or the second one, this CH, OH, CH3. So that's our answers. So 1,2-dichlorobutane, processed from halogenation, that's how we got the butane. This is from hydrogenation, then we got the alkane. And then butan 1,2-diol, that was oxidation from KMNO4, product 3. And we just replaced, instead of the chlorine, we just replaced it with the OH, structural formula. And butan 2-ol, this is when we only have one OH group, and that is the second carbon. Okay, so now let's move on to part C. draw the displayed formula of polybut1ene showing 2 repeat units. Now first let's look at how it will look. So we would usually have C, and then in this case that will be C2H5 because there's butane, and then the next will be hydrogen. So this would be 1 repeat unit, right? 1 repeat unit. So because we want 2 of them, all we have to do is just repeat it. So C, H, and C2, H5, hydrogen, and that's our 2 repeat units. Sorry, 2 marks. Okay. State 1 advantage and 1 disadvantage of using incineration for the disposal of polymers other than effect on climate. So now we can't talk about climate, we can't talk about it, but what we can talk about is carbon monoxide, right? Oh no, that's also climate change, right? What else can we talk about? We know the incineration can lead to toxic substances. Okay. And we know the polymers are not non-biodegradable. Okay, what else do we know? If we were to burn them, so advantage, I'm just going to advantage, these polymers will not take up space. So these polymers will not take up space. Because they're not biodegradable, they will take up space if we don't burn them. Okay, what about a disadvantage? What happens when we incinerate them? We can have toxic substances. So all we have to talk about is that toxic substances may be produced. That is one advantage, one disadvantage. So this is advantage, this is disadvantage. Let's go EI. So this is butane used as the fuel. The equation for complete combustion is shown below. Okay, cool. 35 centimeter cube butane is completely burned in 300 centimeter cube of oxygen. Calculate the final total volume of gas and the same temperature and pressure. Okay. First, let's simplify this. So this would be 1. This would be 6.5. This would be 4, and this would be 5. Okay. So now we have done that. Let's now look at everything else. So first we need to talk about what? We need to look at how much this is produced. So how much this is produced and how much of this is in excess. These are the only gases that are in the total, aren't they? How much carbon dioxide is produced and how much excess oxygen is left. So first let's do the carbon dioxide. Okay, so how do you work out the moles of carbon dioxide? We know that in 1 mole there are 24,000 centimeter cubed of gas, or 24 dm cubed, but in this case we're doing centimeter cubed, so we're going to use this value. So 35 centimeter cubed of butane. Alright, so 35 centimeter of butane. So how much moles is that? So 35 divided by 24,000, that gives us 1.46 times 10 to the power of minus 3 moles, right? Of, this is for what? C4H10. Then we times it by 4, because see over here 1 to 4 ratio. This will give us 5.83 times 10 to the power of minus 3 moles of CO2 produced. Okay, so we know that. So that's good. We know this. Okay, now let's look at excess oxygen. So we use, how much do we use? We use 300 all over 24,000 to give us what? This gives us 1.25 times 10 to the power of minus 2 moles in total. But how many do we only need? We only need this many amount of moles, right? So the excess would be the difference between the two, right? That would be take away this much moles. So 1.46 10 to the power minus 3. This will give us how much? And also, are we doing it right? No, we're not, because see 1 to 6.5 ratio. So we also have to times by 6.5. Okay, so 1.25 times 10 to the power minus t in the calculator minus 1.46 times 10 to the power 3, and we times that by 6.5. So this is multiplied by 6.5. That will give us 3.01 times 10 to the power of minus 3 moles of O2 in excess. Okay, so now it's pretty straightforward. So total volume will be the moles times 24,000, right? So that will be 3.01 times 10 to the power minus 3 times 24,000 plus 5.83 times 10 to the power minus 3 times 24,000 to give us 212.16 centimeter cubed. So that is our final volume. Alright, 1 mark for getting this moles, 1 mark to get this moles, 1 mark for the answer. Alright, let's look at the last question of this paper. Explain the main hazard when using butane as a fuel in a portable heater in an enclosed space. So off the bat, I can think of incomplete combustion, right? In an enclosed space, incomplete combustion. All right, what does this produce? What do we know about incomplete combustion? What can this produce? This can produce carbon monoxide. And how is this bad? How is this a hazard? It's a toxic substance. Which does what? Which is harmful to the body. So harmful to the body. So now let's put this into words. You can say it's a carbon monoxide may be produced as a result of what we said, incomplete combustion, produced due to incomplete combustion. What else can we say? By what? By lack of air, because it's an enclosed space and lack of air. So that's that. What else can we say? You can say that the carbon monoxide, right? How is it harmful to the body? It replaces the oxygen in our cells. So the oxygen in our red blood cells, or you can just talk about hemoglobin. It attaches itself to hemoglobin. It replaces the carbon dioxide, replaces the oxygen in the red blood cells, which can be fatal. So we can say which can be harmful or fatal, which can be fatal. So our two reasons are, so hazard are it may be produced, incomplete combustion, and that it's fatal. Okay, that's the end of this paper. Please be sure to like, subscribe, and share this with people that you think will benefit.